Of course, the focus today will be on discrete probability distributions. We started this last week. I remember I walked you through Bernoulli and binomial. There are other probability distributions of discrete random variable. And of course, today we actually going to be focusing on each and every one of them. Now we advise that you pay attention. But before I get started, I'm actually going to say we concluded the midterm last night, and whatever score you receive, probably for multiple choice, I think for 4101 students, they've been graded fully. 4101 students have been graded fully. And by now, I want to believe you have received your grade. For 5101 student, of course, I'm actually going to complete the grading for 5101 student today. So just wanted to get that as part of information. Okay, so going back into discrete probability distributions, in this particular course, we're actually going to be focusing on Bernoulli binomial geometric discrete uniform and negative binomial distributions. So these are probability distributions of the discrete random variable. You know, it's just like in the United States, am I aware there is a Midwest, Eastern states. Of course, when you want to talk about the Midwest, you talk about Minnesota, you talk about Wisconsin, we talk about Iowa, and so on like that. So we also have probability distributions, okay, for discrete random variable, and those distributions are like members of a family of probability distribution because they model discrete random variable. Of course, after chapter 3, we're going to be going into probability distribution of continuous random variable. Okay, you know, the same way that we have group of states that make up the Midwest in the United States, we also have group of states that make up the Eastern region. Okay, so each of them, I'm actually going to walk you through the statistical properties and also going to cite example from a real life practical situation. So this time around, you know, we are counting down to final. Any other exam that we're going to have right now is going to be final. And you know, that will be done in person. So the opportunity that you have to yourself, where you actually you know, can exploit anything that will make you to succeed is not going to be available when we talk about final, because in the final you are going to be under standard examination condition. So make sure you start preparing. Okay, so I want to before I kickstart, I think I will need to a little bit talk about Bernoulli distribution before coming to binomial. Of course, Bernoulli distribution model a single trial with two possible outcomes, and the outcome could be success or failure. Success with a probability p, and failure with probability 1 minus p. There's so many examples you can cite about Bernoulli trial. For instance, if a doctor conduct a test on a patient, okay, there are two possible outcomes. It's either the patient has disease or not. Okay, so if you flip a coin, it's either you have once. If you flip a coin once, It's either you have head or you have a tail. So there are two possible outcomes. And of course, you have a single trial. And I remember last week, we derived the mean and the variance for Bernoulli distribution. The mean, which we call expected value of S, equal to P, and the variance is equal to PQ. Okay, now going into binomial. Binomial is a sum of Bernoulli trials. You know, I told you the other time, Bernoulli has to do with a single trial. When I say single trial, I mean the numbers of trial equal to 1. And there are two possible outcomes. But when you talk about binomial, on the other hand, binomial is referring to multiple trials, more than one trial. But they are, the similarity between Bernoulli and binomial is that, they are characterized by two possible outcomes. Okay, two possible outcomes. But the difference between Bernoulli and binomial is just like Bernoulli talk about one trial, while binomial talk about more than one trial. I'm going to say that again. Bernoulli focus on a single trial, one trial, while binomial, okay, talk about more than one trial, and the similarity between the two is actually, there are two possible outcomes involved. Okay, so like that, I would advise that you cite example, on your own, to be able to differentiate between the two. Okay, now what I'm trying to show right now is just the probability formula for binomial distribution. And of course, I remember last week I show how the mean, the expected value of S equal to NP, and this is the standard deviation. When the variance is NPQ, where Q is 1 minus P, the standard deviation is the square root of variance. You can see I'm putting a square root on that. If I actually, as a doctor, if I actually have so many patients that I want to get them tested, okay, in each and every patient, it's either they have the disease or not. So when I have more than one patient and there are two possible outcomes, then I'm actually going to use binomial distribution. If I want to figure out the probability associated with that variable of interest. But if I want to figure out what is the expected number of sources that I'm going to have, expected number of sources in a clinical trial is more or less like how many patients on average we have the disease. Okay, on average, how many patients we have the disease. That's what we mean by expected value of S. Expected value of S means the average of the discrete random variable S, and where S follow binomial distribution. And that expectation is NP. N is going to be the numbers of trial multiplied by probability of success. And the standard deviation is going to be the square root of NP to 1 minus P. Now, when you talk about any distribution, we normally want to have a measure of shape, a measure of center, and a measure of variability. Now, what do I talk about measures of shape? Is it skewed or normally distributed? Of course, binomial distribution is not normally distributed. So that is what I mean by the shape. Then I want to talk about the center. What do I mean by center? The center here is the mean, the expected value of S, the average. That's what we mean by center. So the center for binomial is NP. If I want to talk about variability, okay, if I talk about variability, then I should be focusing on variance and standard deviation. So if I want to have a measure of variability for a discrete random variable that follow binomial distribution, I should be more concerned about the variance and the standard deviation. Now, I've just given you example, and I've explained the difference between Bernoulli and binomial distribution. Before I move to other distribution, I think I'm going to have a recap. There's a connection between Bernoulli distribution and binomial distribution. I'm going to say that again. Connection exists between Bernoulli distribution and binomial distribution. So if I have x, if x follow, whenever you see this, we mean by Bernoulli. We mean Bernoulli. Okay, Bernoulli distribution. When x follow Bernoulli distribution with parameter p, okay, the probability of x equal to s is going to be p raised to power x, q raised to power 1 minus x, where s start from 0, 1, the expectation of x equal to p. The variance of s is pq. Okay, I can also rewrite this as p into 1 minus p. Don't forget, q equal 1 minus p. And of course, the standard deviation, okay, the standard deviation of s, don't forget, is the square root of the variance of s. So which is going to be p into that. So if you take a look at this is Bernoulli distribution. So right here, the numbers of triad equal to 1. That is why the support is 0, 1. The support, the x here represent the number of success. Okay, if I try once, it's either I see 0 success or I see 1 success. Okay, this is Bernoulli distribution. Okay, this actually will do a single trial. Why do we call single trial? I mean, the number of trial equal to 1, but they are two possible outcome. There are two possible outcome, which is success and failure. The probability of success is P. The probability of failure is Q. Okay? Now, if I now want to go to binomial, okay, for binomial, okay, we normally write x when you see this, x followed by, okay, with parameter n and p. Here the parameter is only p, okay, so the probability associated, the probability mass function for the binomial is actually n combination x or p raised to power s, p raised to power n minus x. I just wanted to take note of what I have right now. Okay, so when you take a look at that now, okay, I've derived last week the expected value of s equal to np, okay, the variance of s equal npq, that you can also call n into 1 minus that, okay. Now the standard deviation of that, okay, the standard deviation of that is going to be square root of the variance of s, which is equal to np, square root of npq, or you write np into 1 minus that. Now, this is binomial. Binomial is a general form of Bernoulli. Bernoulli is a special form of binomial. Okay, here n equal to 1, the numbers of tri equal to 1, but here, okay, we're actually going to have the support to be 0, 1, 2 until you get to n. So which means here the numbers of triad is more than 1. Okay, that's why you have that. Now, this is my review. Is there any question about the Bernoulli and the binomial before I move to another discrete probability distribution? Is there any question? Okay, now I want to move right now. And I need you to, to pay attention. Okay, I need you to pay attention in case you don't understand. Make sure you ask a question. Now I want to move to geometric distribution. Geometric. Okay, now we're talking about geometric distribution. We are actually all still referring to Bernoulli trials, but this is what happened What is the number of Bernoulli trials that I'm actually going to perform before I'm going to see false success? I'm going to say that again. I want you to see the difference. Bernoulli is different from binomial. Binomial is different from geometric. But the similarity between, among all these distributions is because they are members of discrete probability distribution. That is the similarity they have. Now, coming to geometric right now. Do you know what geometric is trying to say? How many Bernoulli trials? How many Bernoulli trials am I going to have before recording first success? Okay, how many Bernoulli trials? It's just like, I think there was a game last night between United States soccer team and Costa Rica. Did anybody watch the game here? Do you know that very game was played in Minnesota, right? There's a good cup going on, among maybe the CONCACAF or the North American region, the competition going on between Canada, Mexico, Honduras, Costa Rica, United States. The quarterfinal was played yesterday in Minnesota here between United States soccer team men and Costa Rica. And of course, United States won the match, But let's say I didn't watch the match and I want to come to you. Maybe I say, okay, did you watch the soccer game last night? You said, no, 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 no. And somebody said, yes. That's geometric because I'm seeing yes for the first time. Now, the question now is, how many trials am I going to have before recording first success? That is what geometric distribution talk about. How many Bernoulli trials am I going to have before recording first success? Or let's say a doctor actually, they actually get some patient tested, okay, and how the question now is for you to be able to apply geometrical distribution, how many patients am I going to get tested before recording the first one that have the disease? Does that make sense? How many Bernoulli trials am I going to have before recording the first success? That is what geometric distribution talk about. Now, what is the probability mass function for geometric? Okay, the probability mass function for geometric is this guy here. Give me 1 second. Is this guy here? Take a look at that. You see, each of them have different probability mass function. They have different probability function. For geometric is that guy. Okay, for geometric, this is the way we normally write it. We're gonna say if I write this geometric, I'm gonna say the probability of S equal to that. I'm having 1 minus p raised to power x minus 1, then multiply by p, and I have S start from 1, 2, 3, and so on like that. Now, what is the meaning of x? X here in geometric it represents number of Bernoulli trials. But X in binomial and Bernoulli represent the number of successes. So X in geometric does not represent number of successes. So X here, represent numbers of Bernoulli trials. Numbers of Bernoulli trials. And that is why when you take a look at the support, at least we're going to have one trial. At least I'm going to ask one person, did you watch the match last night? At least I'm going to start from one person, and I may continue to go all the way. Okay, why do I keep going? I'll keep going if there is no success. Does that make sense? Exactly what I mean. Now we can derive. Now, how do we find the average? For instance, how am I going to know the average number of persons I'm going to ask in this class before recording the first success, and we have derived the formula for that. It is this guy here. Expected value of x equal to 1 over p. Now, what is p in this case? P is the probability of success. P still remain probability of success, but x is numbers of Bernoulli trials. Does that make sense? And you can see the variance. You can see the standard deviation that I'm actually showing you right now. Okay, now I'm quickly going to do this. Okay, I'm going to derive. Can we derive the expected value of x, the variance of x, and the standard deviation of x for a geometric distribution? You can be given that in exam. You can be given any probability distribution, and they ask you to derive the expectation of x, the variance of x, and so on like that. I need you to pay attention. If I want to derive this, I have to know that expected value of x for any discrete random variable, okay, is this summation x, the probability of s equal to x. Now, for geometric, s start from 1, then to infinity. That is the support. S start from 1 to infinity for geometric. So right now, I'm actually going to have s start from 1 to infinity x. What is the probability function for geometric? Then I'm going to put 1 minus p raised to the power that p. Look at what I'm putting now. What am I doing right now? I'm actually deriving. The expectation of s for geometric distribution. I'm going another example for geometric distribution. Has anybody called to any radio program before? Has anybody called to any? Maybe there's a radio program, and maybe they want to have their opinion from people, and they allow people to be calling in. When you take a call and you call in, they may not pick your call first time, second time, because there's a lot of people calling the radio. Now the question is going to be, what is the average numbers of times I'm going to call before they pick my call? That is what we want to derive. What is the expected value of x? What is the average of the numbers of times I'm actually going to call before seeing the first success? That's what we're deriving right now. Now if you take a look at what I have, okay, you know that Q equal 1 minus P, right? I can do expected value of S equal summation S start from 1 to infinity x Q raised to power x minus 1. Then I put a P outside here because that very P is a constant, right? P is a constant, doesn't depend on S. I bring it outside. Take a look at that. Now, after bringing that outside, please, I needed to pay attention. What am I doing right now? I'm actually deriving the expectation of the binomial of geometrical distribution. How many times on average am I going to wait before recording the first sources? Okay, now it's just like somebody who is waiting for boom in my business. Okay, how many years or how many days or how many months am I going to wait before recording boom in my business? We can use geometric distribution. So what we're trying to do right now is to figure out the formula, for the average. Okay, now expected value of s equal p, okay, summation s start from 1 to infinity. Now we want to go calculus. I needed to pay attention now. Now, in calculus, if I have q raised to power x, q is a constant, raised to power x. If I differentiate this with respect to x, if I differentiate this guy with respect to s, this is what I'm going to have. Do you remember? Do you remember this in calculus? If I have q raised to power x, s is a variable, I differentiate q with respect to x, this is what I'm going to have. Oh, that is what we have here, right? That is what we have here, right? Then I'm actually going to call this guy dq dx. I'm going to call that guy dq dx. Now, if I'm calling that guy the Q dx, so I'm going to have the Q dx. So the Q dx is replacing this guy here. Do you see that? So, oh, sorry. I mean this. Okay, differentiating that. Okay, so I'm calling this. So when I differentiate Q raised to power S with respect to S, this is what it's going to give me. And that's exactly what I'm writing here. Now, you know what I'm going to have? Now, I'll do this. Okay, P, D, ds. I'm breaking it out. Then I'm going to have S start from 1 to infinity, Q raised to power X. If you don't understand, ask question. Final is coming. Final has a huge weight. Does that make sense? Okay, now here I have this DDS, DDS. Okay, now we take a look at this. This is like Q1, Q squared, Q3. Okay, what does this follow? That's a geometric series. Remember geometric series in high school? This is a geometric, okay, series. Now, for geometric series, what is the formula to do sum to infinity? Sum to infinity is A over 1 minus half. The first time divided by 1 minus common ratio. What is the first time here? It's Q, right? The first time is Q. What is the common ratio? Q squared divided by that is Q. Q raised to power 3 divided by that is Q. So the common ratio is also Q, right? Now, when the common ratio is Q, okay, when the common ratio is actually Q, now the next that I'm actually going to have, okay, please pay attention, okay, pay attention. So the next I'm actually going to have, so I'm going to do expected value of S equal, okay, P, okay, DDS into, so using this formula now, it is Q over 1 minus Q. Look at that, okay, Q over 1 minus Q, okay. Now, if I have Q over 1 minus Q, okay. Now, when you take a look at what I have, now, please pay attention, okay. Now, here, initially, I said if I differentiate this guy with respect to S, that's what I have. As you can see here, we have P, D, the Q. So P, D, the S of that, you see what we actually have here. So we have Q over 1 minus Q. Okay, so I need you to pay attention. Is there anyone who doesn't understand what I've done so far? Is there anyone? Okay, now the next thing that we actually want to do, give me 1 second. Okay, so after that, like I said, Q raised to power S is D, the QS, okay, did that. Now, I want to differentiate this guy. Okay, I want to differentiate this guy. Now, in differentiating this guy, I'm actually going to use a quotient rule. Differentiating this guy, if I write this one, differentiate this guy, minus, write this one, then differentiate this guy, divided by 1 minus Q all squared. You know what we call quotient rule? That's what I'm using. So here, okay, 1 minus Q plus Q divided by 1 minus Q squared. So this cancels that. I have P over 1 minus Q squared. So what is that? What is 1 minus Q? Is P. So P divided by P squared. I think that should be 1 minus P. Now, can you see expected value of S? What was that? 1 over P. So that was how we derive the mean. Okay. Now, I'm going to give you a clue to derive the variance, but I'm not going to finish it. okay, because of my time. Okay, now I need you to pay attention. If you want to derive variance, okay, the variance of S is expected value of S squared minus expected value of S all squared. So expected value of S squared minus expected value of S, we got 1 over P, right? 1 over P all squared. So right now, expected value of S squared 1 over P squared. So I need to find expected value of S squared. Now, S squared is the same thing as this. Do you know that? S squared is the same thing as this guy. S times S squared minus S plus S. That will be everything is S squared. So if I put expectation here, I'm actually going to put expectation here, then I'm going to put expectation here. So if I want to find the expected value of S squared, I need to find the expectation of this plus that. Now here, I want to find this guy right now. Okay, plus, what is the expected value of S? 1 over P. So if I want to rewrite, okay, call me back. If you don't understand, make sure you ask me question, okay? If you don't understand, ask me question. Okay? Don't understand, ask me question. Okay, now, right now, okay, now the variance of X, expected value of S squared, the whole of this, expectation into X minus 1 plus 1 over P, then minus 1 over P squared. I want to work on this guy now. So working on this guy for discrete random variable, expectation of X into X minus 1 is summation X into X minus 1, the probability of S equal to that, S start from 1 to infinity. Now, I'm actually going to have S start from 1 to infinity, X into X minus 1. So what is the function? Okay, well, that function is 1 minus P raised to power X minus 1 P for geometric. Okay, then I'm going to bring P out. Bringing P out, S start from 1 to infinity, S into X minus 1. This guy, Q raised to power X minus 1. Okay, now I want to do something again, just like what I did the other time. Okay, now take a look at this. If I have Q raised to power S, if I differentiate, there's supposed to be d dq. Let's see. Okay, the other time I wrote dds. I think it should be d dq. You know why? This guy should be the random variable. S is a constant here. So d dq now, d dq, okay, d dq of S is going to give us this. You remember that? Now, if I go again, if I do second derivative, if I do d squared dqs dq squared, the q squared, okay, I'm doing a second derivative. Now, second derivative of this is going to join it. It's going to be x minus 1, but this time around x minus 2. Can somebody look at what I just did? If I have q raised to power x, if I do the first derivative, is this guy. Second derivative is this guy. But if you take a look at this, here we have x into x minus 1, right? But we have q raised to power s minus 2. But here we have q raised to power s minus 1. I can manipulate. You know why? I can do this and this. Because this can still cancel that. If this can still cancel that, then I can bring this and this together. If I bring this and this together, it's going to be this guy. then the Q here can come here. So right now, look at what I'm going to get. Please pay attention. Pay attention. Pay attention. Now, right now, expectation into x minus 1 will be P. Okay, so right here, I want this Q to come out, PQ. Then I have S start from that to infinity. X into x minus 1, Q, x minus 2. What am I going to write now? Instead of writing that, I'm going to write this guy, the derivative. Please pay attention. You don't understand this question. Okay, so right now, I'm going to have PQ, x start from 1 to infinity. Then I'm going to have d squared qs dq squared. Do you see what I just write? So this guy, the second derivative, is replacing that guy. Now, you know what I'm going to do again? Here, I'm actually going to have PQ. Okay, now d squared dq squared is going to come out. Then I'm going to have q raised to the power x. You remember what I did the other time? Sum q raised to the power x, using the sum to infinity. It's a geometric series. So this guy here, okay, using a over 1 minus r is going to be q over 1 minus q, right? Now, if I want to write this, I'm actually going to have this d squared, the q squared, then q over that. So which means I'm going to differentiate this one time, second time, because of this derivative, the second derivative. Okay? Now, please pay attention. Okay? Pay attention. Okay? Now, you know, this is where we're coming. Whatever we get, we're going to plug it here and simplify. Now, right now, so expectation into x minus this PQ, I want to differentiate this one first time, the second time using quotient rule. The first time, 1 minus Q, differentiate that 1, minus Q into negative 1 divided by 1 minus Q squared. Now, when I differentiate first time, that is going to reduce to dq. You can see, instead of d squared, dq squared, because I've differentiated first time, this is going to go to first derivative. Now I want to simplify this and differentiate again. Okay, so I'm going to have PQ. So right here, 1 minus Q plus Q divided by 1 minus Q squared. Okay, this cancel that. So right now, I got, don't forget you have d dq. Okay, so PQ, d dq. Okay, this is 1 over that. Okay, and it's going to be PQ d dq. Okay, 1 minus q raised to the power minus 2. Okay, 1 minus q raised to the power minus 2. Then I'm going to differentiate this guy now. Okay, I'm going to differentiate that guy now. Okay, I'm going to differentiate that guy now. So I want to differentiate this guy. How do I? This is a composite function. So here I'm going to have expectation into x minus 1, PQ. Differentiated this one, okay, negative 2. The negative 2 will come down, block it. Differentiate what you have inside, negative 1. Negative 1 will come out. Then you write the whole of this. Okay, 1 minus q, then raised to the power minus 3. Okay, so now what do I have here? That will be 2pq. Okay, and that guy is the same thing as this. Raised to the power 3, because a negative 3 up. Now, here, I'm actually going to have, what is 1 minus q? That will be p, then raised to the power 3. So this cancel one of that. I'm actually going to have 2q divided by p squared. Okay, 2q divided by p squared. Now I'm gonna plug, because what I just derived here, is just this guy. Okay, so I'm gonna plug in this guy here now. Okay, now I'm gonna plug the guy in now. I need you to see what I'm doing. I'm going to plug the guy here now. Okay, so right now, the variance of x, so instead of this, then I'm going to write 2q over p squared. Okay, 2q over p squared. Okay, then plus 1 over p minus 1 over p squared. Then I'm just going to find the SAM, p squared. Okay, that would be 2q p minus 1, right? Now, I want to simplify this. Okay, if you take a look at the variance, okay, 1 minus p over p squared, right? Okay, so if you take a look at this, 2, so instead of q, 1 minus p plus p minus 1 divided by p squared, so it's going to be 2, okay, 2, negative 2p plus p minus 1 divided by 2 squared. 2 minus 1, 1, negative 2p plus p. That. Can you see that? That is the variance. Okay? And of course, the square root of that is just going to be, the square root of that will be standard deviation. Now, I quickly want to move. Let's move to the example. This is an example on that geometric. The probability of a successful optical alignment in the assembly of optical data storage product is 0.8. Assuming the trials are independent, what is the probability of first? Look at that. First successful. That's how you're going to recognize geometric. When they ask a geometric question, be looking for first success. Okay? You can see requires exactly 4 trials. The second one said, what is the probability that the first successful alignment require at most 4 trials? The third one said, what is the probability that the first successful alignment require at least 4 trials? Now, you know, what is in display here is just what is the difference between exactly 4, at most 4, and at least 4. That is what we just wanted to, we want to test. Now take a look at this. Now, what is the formula here? Okay, here you're actually writing the formula. It is P into 1 minus P, okay, raised to power X minus 1. You know, that is a probability mass function for geometric, but they've given you P to be 0.8. If you come back here, look at that. A P is 0.8, okay? And they say they require exactly 4 triad. Don't forget, in geometric, numbers, X represent numbers of triad. Now you plug in 4 here, 4 minus 1, 3. That was why you have that. You know, if P is 0.8, 1 minus P will be 0.2. Now, is there anyone who doesn't understand how they figure this out? That is exactly 4. When they say at most 4, at most 4, okay, it's going to be less or equal to 4. Less or equal to 4. Where does it start from? Where does, the support for geometric start from? It starts from 1. Don't forget, 1, 2. So when they say x less or equal to 4, I'm actually going to do what is the probability of s equal to 1, s equal to 2, s equal to 3, s equal to 4. I will use the geometric formula. Then add them up. That will give me this. And when they say at least 4, please pay attention. At least 4 means 4 or more. And if you want to go by 4 or more, you're going to go forever because this goes to infinity. Can you see that? And that's why you need the law of complement. Now take a look at this. When I say at least 4, it is the same thing as 1 minus the probability of s less than 4. They are complementing each other. And when I say s less than 4, you know what that means? S less than 4 is just going to, you mean this. S less than 4 will be 1, 2, 3. Does that make sense? Now, at the end of the day, when you do that, you get this one. Subtract that from 1, that will give you this. That's super easy. Okay? Now, I want to move right now. If you pay attention to another one, this is another example. Assuming that each of your calls to a popular radio station has a probability of 0.02 of connecting, that is, of not obtaining a busy signal, calls are independent. what is the probability that the first call, look at that again, first. Whenever you see first, you have to use geometry. Connect is your 10th call. Oh, your 10th call will be the one that will connect. 10th call, it means S equal to 10. It means you need 10 binary trials. Okay? Then it said, what is the probability that I require more than 5? What is the mean numbers of calls needed? Mean number of calls needed. Now, if you want to do the first one, S equal to 10, plug in into geometric formula, you're going to have that. For S greater than 5, don't forget, S greater than 5 will be 1 minus S less or equal to 4. Then what about the average? Oh my God, the average is easy. You are just using 1 over P. Okay? They gave you P to be 0.02. 1 over 0.02, okay? That will give you 50. 1 divided by, so that is that, about that. Any question? Now, because of my time, I'm actually going to move. Negative binomial. Now, pay attention. Negative binomial is a general form of geometric. The same way, binomial is a general form of Bernoulli. Negative binomial is a general form of geometric. Now, what is the difference? This is different. Geometric is going to say, how many Bernoulli trials am I going to have before recording the first success? But do you know what negative binomial is talking about? How many Bernoulli trials am I going to have before recording a good number of successes? Does that make sense? Which means we're not seeing success for the first time. They've been seeing success. So now the probability mass function is going to change. Take a look at that. We have two forms of probability mass function. It's going to be x minus 1 combination r minus 1 p raised to power r 1 minus p raised to power s minus r. X here still remain numbers of Bernoulli trials. But what is r? R success. R represents the number of success. Okay, R is not equal to 1. If R equal to 1, if you plug in R to be 1, then you are going from negative binomial back to geometric. Does that make sense? Now, are you surprised? Look at the mean. What do you see? In geometric, what was the mean? 1 over P. But in negative binomial, R over P. R represent, we're talking about R success. We are not seeing that for the first time. So please pay attention. Look at this guy here. Compare with this guy here. Look at that. Then you're going to see that if you come here and you plug in R equal to 1, then you will go back to the geometric. That makes sense? Now let's look at the example. Okay? Let's look at the example. Suppose S is a negative binomial variable with P equals 0.2 and R equal to 4. Determine the following. They want you to determine the following. What is the expected value of X? What is the probability of S equal to 20? What is the probability of S equal to 19? It's going to be easy. Look at that. I found to find the expected value of X. R over P. They're giving you R. They give you P. Plug them in. Then in the formula, S equal to 20. Plug it into the formula. Okay, you're going to get that. S equal to 19 or whatever you plug in into the formula, you actually going to get that. What formula are we using? We're using this formula here. Can you see that? That's the formula we're using. You have to know what your X represent, what your P represent, and what your R represent moving forward. Okay, does that make sense? Okay, so that is an example on negative binomial. But you know what? Because of my time, I'm going to start from here tomorrow. Well, today, what have we achieved? We've achieved Bernoulli, binomial, geometric, negative binomial, 4. Now, Bernoulli, we use Bernoulli to model a single trial with 2 possible outcomes. We use binomial to model multiple Bernoulli trials with two possible outcomes. We use geometric to model, okay? Uh, we want to figure out how many Bernoulli trials I'm actually going to have before recording the first sources. What about negative binomial? We use negative binomial to figure out how many Bernoulli trials are we going to have before recording a good number of successes, not just the first success, which means you are not seeing success for the first time. But you know what we're going to continue doing tomorrow? I'm going to focus on more discrete probability distribution, like discrete uniform and Poisson distribution. So before tomorrow, you can be reading that. That's a probability distribution for discrete uniform. I'm going to derive how do we arrive at that for mean, how do we arrive that for variance. So I will advise that you look at this material ahead of time. That is why I'm actually going to start from tomorrow. And I'm also going to show you how we can generalize negative binomial using geometric distribution. For instance, you remember on Thursday, when we derive the mean and the variance of Bernoulli distribution, we are able to deduce the mean and variance of binomial from that. So what I'm also going to show you tomorrow, okay, if I know the mean and variance of geometric distribution, how can I derive the mean and variance of negative binomial? Because they are connected. Okay, negative binomial is a general form of geometric distribution, as binomial is a general form of Bernoulli distribution. We're also going to use the same idea tomorrow. Before I go today, let me tell you this. How did I find this easy? I found all of this easy because I relate them to real life. I just told you right now what Bernoulli represent, what binomial represent, what geometric represent, what negative binomial represent. I'm going to say it one more time before I go. When can I use Bernoulli distribution? I'm going to use Bernoulli distribution when I'm only interested in a single trial with two possible outcomes: success, failure, and they have their respective probability. When do I talk about using binomial? Oh, I'm going to use binomial when the number of Bernoulli trials is more than one, but I still have two possible outcomes, which means binomial is a generalization of Bernoulli. Then I want to go to geometric. In geometric, when do I use geometric? I'm going to use geometric if I want to figure out how many Bernoulli trials am I going to have before recording one success, the first success. That's what I use geometric. When do I use negative binomial? How many Bernoulli trials am I going to have before recording a good number of successes? Does that make sense to you now? It's just like in the negative binomial. Oh, if I didn't watch the game last night, and I want to ask from you whether you watched the game last night, how am I going to know that's a negative binomial? If someone said no, 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 yes, no, 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 another yes, no, 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 another yes, that's a negative binomial. That's no longer geometric because I'm seeing more than one success. Okay, and if I want to count the number of successes, R in the formula represents that. R in the negative binomial formula represent, when you see that's why you see R here. R represent the number of successes. X represent the number of Bernoulli trials. This way I'm going to stop. Make sure you all stay safe and have a lovely day. See you tomorrow. Bye for now, everyone.